Can you
Okay.
see?
Yes, we can see the
Okay.
slides. Excellent.
Okay. Thank you.
Okay, so welcome to the second talk in the afternoon. And the speaker is María Cáceres and from University of Granada, and she's going to talk about some PDE models for neural networks. Maria, please.
Okay, thank you very much, and thank you also for the invitation. I want to speak about some PDE model for neuronal network, and this is in relation with the design relation because it's other kind of model, different of Susan talked yesterday. And also, I want to focus my talk in the blow-up phenomena for the nonlinear electrical model, which is the subject of the previous talk. So let me start with something that I think you know, but since the talk is about the neuroscience, I have to start saying that the neuron is an electrically excitable cells of the nervous system that process and transmit information through electrical and chemical signals. So neurons are connected across synapses, and it's happening at the level of the membrane of the cells. So to try to describe the mathematical models or the PDE models to describe the membrane potential, first we have to say that the membrane potential is the difference between the voltage inside and outside of the cell, and there are different concentrations inside and outside of the membrane of the cells of the neurons, because there are different ions inside and outside of the cell. So there are also channels in the membrane, and this will change the concentration of ions inside and outside of the cell. And as in the talk of Pierre, what's happening is when the membrane potential arrives to a threshold value, emit an action potential, and the membrane is depolarized, will be reversed. And when this happens, we say that we have spikes. Okay. So are there different scales to understand this kind of model, or to try to describe the membrane potential of the neurons? And you know very well that we can think in the neurons as particles, so we have the microscopic description, or we can think in the mesoscopic scale. In this case, the unknown is the probability density to find the neurons with some variable. In kinetic theory, we know that it's space and voltage, but in this case, we can think in this family of models that the variable could be the voltage or the conductance, or also the elapsed time from the last span. And also there are other PDE descriptions to describe the macroscopic quantity in this case for neural model. This macroscopic quantity can be defined. So before I start, I would like to say also that there are relations between the neurophysiological phenomena and the property of the solution of the different models. For instance, synchronization of or asynchronization of the network is related with the blow-up phenomena with periodic solution with asymptotic stability. For instance, ellipses, epilepsy can be related with blow-up phenomena, and also the multi-stability of the solution of the steady state can be related with visual perception and decision making. For example, I'm pretty sure that you know this kind of picture where you can see different things in the your preference if you want. For instance, here, I don't know if you see an old woman or a young woman, or in this one, if you see two faces, or if you see here a cup or a base. Okay? So this kind of situation is related with stability solution. Okay, so what is the outline of my talk? I would like to start with some background in order to understand exactly what is the family of a PDE model or a stochastic differential equation if we think in the microscopic description. And I will focus my talk in the nonlinear non-selected integrated model, as in Pierre's talk. I would like to present briefly the family of models of in this with these 9 and what is now. I would like to focus the attention on the blow-up phenomena and try to answer what happened after the blow-up phenomena. And to do that, we did an analytical study because with the PDE description, we are not able to know what happened after the blow-up phenomena. So we go back to the particle system and try to see what happened. And I will finish with some conclusion and working progress. Okay, so first, the starting point of this kind of model is the information that gives us LAPEC when we say that the membrane potential can be modeled as an electric circuit. So this means that we have this relation between the evolution of the voltage and the current. Okay, so the question is, who is the applied current? And we can split it in 3 parts, which is the leakage part. We have only this part, the membrane potential relates to the leakage part and to the leakage value, and we have to take into account also the ions, the current given by the ion channels and the external current. So if we think in the description in terms of the ion channels, the typical model is the Hopkins-Hartley model, but this model for each neuron have to account 4 equations, ordinary differential equation, nonlinear, and this is very expensive to do simulation with this. And so there are 2 simplifications. The first is the Morris-Lecard. In this case, there are 3 equations for every neurons, and the Fitzhugh-Nagumo model have 2 equations for every neuron. But in these 3 cases, they are very complicated to the simulation, so it's typical to consider a more simplified model, which is called the integrate and file model. If we consider only the voltage, we have the integrate and file model. If we have the conductance as the other variable, we have the integrate and file model. We focus in the integrate and file models. Okay, so as I said before, we have the leakage part and the current, and we have to remember that there are sometimes we call it time spike or filing time spike. That means that the voltage of the membrane potential arrive to the V threshold, admit the action potential, and then go to the V reset. So the situation is something like in this picture. Okay. So the question is, what is I? And I represent the interaction of the neuron with the network. And so we have a spike trains which follow an stochastic process. And if we consider the mean field limit, we can obtain this kind of families of PDE models. First, P is the unknown and is the probability to find a neuron at time t with different variables. For instance, if we consider a Poisson process, which means that we don't have to account the path of the spike, we have the nonlinear focal plane equation. In this case, P is the probability to find a neuron at time t with voltage V. In this paper, you can find the origin of this kind of focal plane equation applied for neuroscience in comparison with the experiment and so on. But also we can consider a more general point process that has to account the memory, and in this case that we obtain is in the limit is the H structure partial differential equation that was studied first by Pagdaman, Pertan, and Salon. In this case, P is the probability density to find a neuron at time t with a state S, and in this case, the state is the time elapsed since last spike. Well, there are also some works trying to relate both models. at least in the linear case, done by Dumont, Henry, and Tarnefeld. Okay, so, but as I said you before, in this talk, we are focused on the blow-up phenomenon. So the question is, what does family of models exhibit this phenomenon? Well, the blow-up phenomena, we observe it for the nonlinear focal plane equation that was presented in the previous talk. Because sometimes the firing rate diverges at finite time. Okay. For the H-structure partial differential equation, the firing rate does not diverge at finite time, so there are no blow-up phenomena. And for the nonlinear focal plane equation, including conductance, also the firing rate does not diverge at finite time, and there are no blow-up phenomena. Okay, so we focus the rest of the talk in the nonlinear focal plane equation where the blow-up phenomena appear. Okay, so what about this model? As in the previous talk, if we assume a network sparse with random connectivity with n neurons and a small synaptic strength compared to the firing threshold, and every neuron spike according to a Poisson process, and we consider the number of neurons tends to infinity, we obtain two possible family of models to describe the behavior of the network. The microscopic description was studied by Delarue, Angers, Ravendrala, and Tantre, and the macroscopic description that we studied the analytical property of these kind of models. And I want to summarize now the result that we know. But the result is similar for the stochastic differential equation, the microscopic description, and for the PDE description. Okay. So this kind of model takes into account neuronal phenomena. The more important ingredients are networks are composed of excitatory and inhibitory neurons. And when the membrane potential reaches the threshold value, we call it BF, the neurons emit an action potential, which is the spike, as I said before, and then their voltage value return to a reset value BF. And between the emission and the reception of a spike among the neurons, there are some transmission delays. And also during a certain time, we call it refractory period, the neurons do not respond to stimuli. Okay, so with this ingredient, we have a family of nonlinear legitimate models. In the previous talk, we consider the first one, which is the simplest one. So we consider only one population innervating excitatory or innervating inhibitory. If we can add one ingredient more, so we have included the refractory state, and this means that at the focal plane equation for one population, we have to add an ordinary differential equation to describe the refractory state. And if we want to take into account the network composed by excitatory and inhibitory neurons, we have to add other focal plane equations, which are coupling both. And if we want to take into account the full model, we have to include it two equations for the refractory state. So the full model is two focal plane equations plus two ordinary differential equations for the refractory state. And there are some extensions also for this kind of model. We studied also the possibility of randoms of discharge potential, which means that the neurons can spike not in the fixed value of the threshold. The neurons can spike in the random region close to the threshold. Okay? And also, as I said before, we can include it also the conductance in the integrated fine model at the beginning and obtain a nonlinear focal plane equation with the term of the voltage and on the conductance. So, as I said before, I want to speak about the blow-up phenomenon. So we will focus on the simplest model in order to understand what happened after the blow-up. So this means that we consider only one population, innervating excitatory or innervating inhibitory, and sometimes we consider the transmission delay in order to avoid the blow-up. So What is the model? The model is the model presented in the previous talk. We have this focal plan equation with the drift term. We keep in mind the parameter B, which is the connectivity parameter, which means that if P is positive, the citatory is the network is inaveraging excitatory. If P is negative, the network is inaveraging inhibitory. The diffusion depth, we can consider that is constant, but can be dependent also of the firing rate. And in the right-hand side, we have the fact that when the neurons arrive to the D threshold, emit a spike and go back to the D threshold. Well, we have the typical boundary condition, because when the neurons arrive to the D threshold, go back to the D reset, we have that in the D threshold, the P is 0, and in plus infinity, in minus infinity is 0 also. And the system is nonlinear because the firing rate is computed in terms of the derived of P in terms in the B threshold. Okay, so the model is nonlinear. Okay, so what is now? First, about the system result for the inhibitory network, which means B negative, they are global system. For the excitatory network, could be blow-up phenomena and the transmission delay about the blow-up. I'll try to explain it in more details in a few minutes. For the steady state, that we know is that for the inhibitory network, there are a unique steady state. For the excitatory network, depend of the value of the connectivity parameter B, which is positive. Could be one, 2, or no steady state. About the asymptotic behavior, as Pierre said before, we know that there are exponential convergence to the steady state, which is unique because we don't know, we only know the convergence to the steady state if the connectivity is smaller, is very small, and in this case we have only one steady state. And about periodic solution, we studied previously with Pierre's talk. And of course, all these results are extended for the full nonlinear related integral time model, which means 4 equations, 2 focal plan equations for the excitatory and inhibitory activity in neurons, and 2 ordinary differential equations for the refractory state of excitatory and inhibitory neurons. So, what about the blow-up? Well, the first result in this injection that we did say that for the excitatory network, the solution can blow up when, if we fix the parameter B, if the initial condition is concentrated enough, we have blow up, which means concentrate enough. We need to obtain the blow up that this inequality holds. And if we see, if we think, for instance, that the initial data here is something which is very close to a Dirac delta in the threshold, this inequality is true, and we have the blow-up phenomenon. But if we fix the initial data and we see this inequality, if we take B large enough, this inequality is true, and we have also the blow-up phenomenon. Okay, the proof of this result is by contradiction using an exponential moment of P, this exponential moment of P, and seeing that this exponential moment is bigger than an exponential function in T, and this is in contradiction because this is bounded because P is a probability density. So after that, the result was extended by Pierre and Delphine, because they proved that for the large, independent of the initial condition, we have blow-up. And for B large, they are in general, there are no steady state. And so that happens in this situation, without delay, the system blow up. Okay. So what was the criterion to globalize system, or in other words, to have blow up? Well, the criterion was given by Carrillo, González, Gualdani, and Schoenberg, and they say that we can obtain a solution if the global solution, if the firing rate doesn't vary in finite time. Okay, and they prove it that this is the case for the inhibitory case, but of course for the excitatory case we have no global solution because we know that they are blow up, and we observe it numerically that the blow up is a consequence of that n evidence in finite time. Okay, so what happens if we put delay in the system in such a way that we have is the system is linear during delay periods of time. And in this movie, you can see what happens if we don't put delay, which is this case. The solution go to the B threshold in this case is 2, and the B reset is 1. So that we observe it without delay is that the neurons go to the B threshold and go back to the B reset, and we can continue with the PDE description, the simulation, because n diverse in finite time. But if we put the delay, that happens is in this case where B is small, the solution goes to the stable state with the delay. Okay. And in general, that we observe numerically is that if B is small and we have only one steady state, as I said before, the solution goes to the steady state. But if B is large, in the case that there are no steady state, that happens is the firing rate is increasing. So in order to prove the global system, we found some difficulty to prove it, because in the previous result by Carrillo, Gonzalez, Gualgani, and Schoenberg, they proved the global system for the inhibitory case because the firing rate is uniformly bounded for every time. Is uniformly bounded. But in the excitatory case, this is not the situation because as I showed you before in this picture, the firing rate is increasing. So we can, it's not true that it's uniformly bounded. Okay. So to prove the global system, we follow a similar strategy as in the case without delay in the inhibitory case. And we regrade up a Stefan-like problem, which means that we have a free boundary, and the free boundary is in relation with the firing rate. And then we prove the local system in terms of the fixed point for the firing rate using an integral formula. And we use the K result of the maximal time system. But in this case, since the firing rate is not uniformly bounded, we have to use the super solution to prove the global system. So now we ask it what's happened after the blow-up phenomenon. Okay, and to answer, as I said you before, we study numerically what happened at the level of the microscopic description. So we consider a particle system, and we have a typical neuron described by this stochastic differential equation that I wrote here in the terms of the firing rate, because it's the firing rate which appear in the PDE description. So remember, when the voltage arrives to the B threshold, immediately after go to the B reset, and this is the time spike. Okay, so the relation between the firing rate with the microscopic description is we have the sequences of the spike, and we can consider the theoretical expected number of spike times by a typical neuron, and which is C1 in the case of classical solution, and we can derive, and exactly the firing rate of the PDE model is the derivation of the expectation. Okay, so with this, we do some numerical experiment, and that we observe is that sometimes appears a new profile, which is the plateau distribution, which means that after the blow-up, in situation of blow-up, the membrane potentials tend to be uniformly distributed in the interval BR-BF. In this picture, this is BR 1 and BF is 2. Okay, so that we observe it is that the system, the behavior of the system after the blow up depends of the connectivity parameter B. To be more precise, if the B is smaller, we say weakly connected network. If smaller, it means that is B, the connectivity parameter is less than the difference between the B threshold and the R. The solution, the system tends to its unique steady state after the blow up. But in the highly connected network, which means that the connectivity parameter is bigger than BF minus BR, plateau distribution appears when synaptic delays are taken into account. To be more precise, when there are no steady state, the system tends to a plateau distribution with synaptic delays are taken into account. In the case that we have two steady states, we have the bistability between the steady state with the lowest firing rate and the plateau state. And in the limit case, it's interesting because in this case, the system tends to a plateau distribution if we have a small delay or without delay. And if we put a large delay, that happens is the system tends to the stationary solution. Well, at the microscopic level, the notion of solution was extended to physical solution by Delarue and Rotendler and Carré. And let me explain you a little bit what is the difference between physical solution and classical solution. Well, for classical solution of the stochastic differential equation, as I said you before, when the membrane potential arrives to the B threshold, spike and go back to the B reset. And the expectation in C1, in particular, our firing rate is continuous. But for the physical solution, the difference is that the neurons can spike a little bit before BF. A little bit before, it means that if the voltage arrives to this quantity, where delta A is the discontinuity of the expectation. And to obtain a physical solution, it's necessary that the sequences of a spike have to be increasing and cannot accumulate in finite time. So let me explain in a little more details. So physical solution means that we can have jumps of the expectation. But these jumps have to be in such a way that the neurons cannot fire more than once at times. To obtain that, we need that the connectivity parameter is small, so it's exactly the range of the difference behavior that we found after the blow-up phenomena. So B have to be less than the difference between B threshold and B reset, and the jump have to be with this expression that can be seems a little bit strange, but let me explain you what happened with the particle system. With the particle system, the jump, in order to have physical solution, have to be the proportion of neurons that are spiking at time t. Okay, and this is exactly this expression here is exactly the number of neurons that are spiking at time t, and is the discretization of this expression for the NNLIF limit. Okay, so what happened is that in order to have uniqueness, we have to use the cascade mechanism, which say exactly how to order the spike in the sequence of the spike in the physical solution. So, of course, a classical solution is also a physical solution because in this case there are no jumps. And I think I forget to say before, but when the physical solution arrives to the B threshold, go back to something which is bigger than B reset. So in some sense, could we understand that the solution go to the B reset and feels a kick and increase a little bit the voltage, but in such a way that it's not enough to go to the B threshold again and spike at the same time. Okay. So this is exactly the condition for the YAM in order to avoid this. Okay, so summarizing this difference between the classical and physical solution, we say classical solution are continuous, the expectation are continuous. For physical solution, the expectation present discontinuities. So for classical solution, the neurons only fire when they reach the threshold. For physical solution, neurons can fire if their membrane potential are close to this threshold, but less than the threshold. And about the system, there are no global system for classical solution in such a way, in the same way that in the PDE description, without delay, of course. If we put delay, we have global system for classical solution also in the macroscopic description. And for the physical solution, there are global systems. Okay. So this means that the solution can continue after the blow-up phenomenon. Okay, so if we think in this in terms of our numerical simulation, the notion of physical solution makes sense only for weakly connected network, which means B smaller than B, the difference between BF and BF. So for physical solution, what happens after the blow-up is that the system tends to its unit steady state after the blow-up. And for the limit case, it's interesting because the plateau profile can be understood as a stationary profile when n tends to infinity. I will explain you in more detail in a few minutes. What happens is the system, in this limiting case, the system tends to a plateau distribution and the blow-up situation, either without synaptic delay or with a very small delay value. And the system tends to the stationary state for a high enough delay. Okay, so let me show you now the simulation. In the rest of the simulation, the B reset is 1 and B threshold is 2, and the diffusion coefficient is 1. So this is what happened with our simulation with the PDE description. In the situation of blow up, we can continue because the firing rate diverges and we don't see what happened after the blow up. If we put delay, that we observe it is that if B is smaller, the firing rate relaxes to the steady state, and because we have in this case only one steady state, and if B is large without a steady state, the firing rate is increasing but doesn't diverge in finite time. Okay, what can we see? We see with the particle system. Well, in the blow-up situation, if we consider physical solution, we observe it that we started with something which is very close to the big threshold, and we observe it that the system evolves to the steady state. And we observe it that the solutions are physical because this is the expectation at the moment of the blow up, and we observe it that the expectation is discontinuous. Okay, so after that we observe it that the expectation is increasing, of course, and the rate of growth is constant, which is exactly the firing rate of the steady state. Okay, so we observe it how after the blow up, the physical solution continues, and the solution are physical because we have a discontinuity of the expectation. Well, where B is large, so non-physical solution, that we observe is that could appear that we call it trivial solution, which means that the neurons evolve up to the B threshold and then go back to the B reset and continues in this way all the time. So they go to the B threshold, go back to the reset, and B is large, so have the energy, if you want, enough to arrive to the B threshold. Okay. So under what situation do plateau state appear? Okay, for the limit case that we see is that if we don't have delay, the system evolves very fast to the plateau distribution. We see here the evolution, and with this movie we see very fast go to the B threshold and then go to the plateau distribution. We in the middle of the movie we change the variable because here we started with something until 12, and at the end the plateau distribution is in the value 1, of course. So we observe it how go to the B threshold and then go back to the B reset, and immediately very fast go to something which is the plateau distribution. So it's uniformly distributed between the B threshold and the B reset. Okay, if we put a very small delay, the situation is very similar. Go to the plateau distribution also. But if the delay is large, that happen in this limiting case is that the solution goes to the stationary solution. Okay. And what happened in the case that we have two steady state? In this case, as I said you before, we have a bifurcation, the stability between the lowest steady state, which means the steady state with the lowest firing rate, and the plateau distribution. I put here the situation of the plateau distribution. As before, if we consider a large delay, we go to the plateau distribution, and the firing rate is increasing, but less than if we consider a smaller delay. In this case, the firing rate is increasing, doesn't divert. We know that there are global solutions because we are taking into account delay, but the firing rate is increasing and go also to the plateau distribution. And in the case that there are no steady state, that we observe it is that the solution, if we put delay, goes to the plateau distribution. Okay. So to finish, I want to speak a little bit about the plateau formation. Well, we are studying this, what happened, and we will try to do something analytically. So let me go back to the steady state as in Pierre's talk. The steady state is given by this expression. Okay, it's something which depends of the stationary firing rate. Okay, and we call it here an infinity. Okay, so this is the steady state, and that we observe is in the evolution of this situation, which, for example, here where there are no steady state, this profile looks like something that we call it pseudo equilibrium. Pseudo equilibrium, which means we consider for n given this profile, which is very close to the steady state, but is not the steady state, because in this case we take n fixed, we put here, and we obtain n infinity in such a way that this profile has mass 1. Okay, so we call it this pseudo equilibrium, and if we observe it in this picture, we represent this pseudo equilibrium for different value of n, and at the end, when n increases, this is very close to the plateau distribution of the simulation. And also, if you see this picture here, this try to evolve to thanks to this pseudo equilibrium, and at the end, when n goes to infinity, go to the plateau distribution. Okay, so it's true that the plateau distribution can be seen as a limit of this pseudo equilibrium when n tends to infinity. Okay, and the relation between the pseudo equilibrium and steady state is clear. A pseudo equilibrium is a steady state if and only if the n is the n infinity. Okay, It's interesting the limit case of the physical solution, because in this case, when B is equal to difference between B threshold and B reset, the plateau distribution is a steady state when n tends to infinity. So in this case, equilibrium and plateau and pseudo equilibrium when n tend to infinity. So this is the plateau distribution is the same. Okay, so in this sense, for B equal to the difference between B threshold and BR, we have two equilibrium. One is the typical stationary solution, and the other one is the plateau distribution. Okay, so we are working in progress in this subject, and in collaboration with Canizo and Ramon. I want to present two works in progress. The one is try to answer the question, can we prove convergence to plateau state? And to try to answer, we try to work with the entropy method, but the entropy method doesn't work. As in the talk of in the Pierre's talk, we have a problem with the bad term. The bad term is the term with the bad sign of the entropy dissipation. And in order to do something, we need that the B is smaller. But so thinking in what's happened medically, we think what's happened if we consider last delay. So in such a way, we have the delay periods as a sequence of pseudo equilibrium. So we are working a new strategy to prove the convergence to the equilibria in the case of large delay. And to do that, we need solution to be uniformly bounded, and this is a problem with the plateau distribution. So we have to work a little bit more to prove the convergence to the plateau distribution, but could be another strategy to prove the convergence to the steady state without the restriction of P smaller but with large delay. And other work in progress is try to answer the question, what happens if neurons do not respond to stimuli during first reset time, which is the refractory period. Numerically, that we observed is that it looks like that after the blow up, all the it makes sense the concept of a physical solution without the restriction of B, because the neurons remain a certain time in a refractory period. So it's not possible to spike twice at the same time. And that we observe it after the blow up, the system tends to a stationary state for B small. Here is the situation. And we observe also periodic solution in the case of B large. Here is we observe that we have the singularity, the n diverse in finite time, and so it's a physical solution. And that we observe is the neurons go to the threshold, and then go back to the B reset and relax and diffuse and have take some time to go again to the threshold, and we have periodic solution in this sense, which without the transmission delay. So it seems that this is a consequence of the blow-up phenomena and the physical and the global solution for physical solution. So conclusion to finish, a kinetic model describes neurophysiological phenomena, and this talk focused on blow-up phenomena, which can happen for nonlinear legacy integrated file model if there is connectivity between excitatory neurons with or without refractory state. No blow-up for one averaging inhibitory population, or if there is transmission delay between excitatory neurons. Well, physical solution for the stochastic differential equation are global on time. We wonder what happened after the blow-up phenomena, and to answer, we study numerically the particle system, and we observe that the system continues after all neurons fire at once, and sometimes systems tend to a plateau distribution after the blow-up. which means that the membrane potential is tends to be uniformly distributed between the D threshold and the D reset. What happens after the system depends on the connectivity parameter B after the blow up. Without delay, for physical solution, which is B smaller, the system is reversed to the D reset and then to the steady state. And for B large, the system collapse and tends to a reverse state that I said before, go to the B reset and immediately after go to the B threshold. And in the limit case, tends to a plateau state. But if we put delay, and in this case, we know that there are global solutions, for B large, the systems tend to a plateau distribution, even when there are no steady state. And in the limit case, tends to a plateau distribution if the delay is small, and tends to a steady state if the delay is large. Well, work in progress is physical, try to see what happened with the physical solution for the refractory state, as I said before, and we prove convergence to plateau state. And other interesting question is, what is the meaning of physical solution for the partial differential? To finish, I want to thank all my collaborators, José Antonio Carrillo, Benoit Partin, Ricardo Schneider, Pierre Roche, Delphine Salor, Alejandro Ramon Lora, in relation with the nonlinear elliptic integrated model, but also Listau for the non-Fokker plan equation with conductance, Julien Chevalier, Marie Dumic, and Patricia Reynaud for the past the relation between the microscopic and the macroscopic description using point process for the training spike, and also Nicolás Torres for some paper with the H structure, one paper about the H structure in the equation. So thank you for your attention.
Thank you for a nice talk. Questions? I have a quick question. Is there any theoretical work linking the microscopic to the macroscopic, like a mean-field limit?
Well, the work that I sent you, showed you before with Chevalier, she continued working about it for the H structure partial differential equation, and there are some papers also for the integrated transfer models. Yes.
Okay. All right. Other questions?
So I did not understand, Maria. Can you find these plateau solutions for the continuous model, or is it only that you find that for the particle system?
No. For the continuum model also. In fact, when did it simulation for the delay for the PDE with delay, yeah, and we find this simulation, we observe the plateau distribution also.
Okay, thank you.
Okay.
Maria Jose.
Hola.
So, can you interpret how can you interpret the plateau solution? What would be the best way? I mean, you said synchronization. What wouldn't it be that is like continuous blow up of the neurons because they just go directly from B reset to BF?
Yeah, but this, well, I don't think so, because this is exactly what's happened here. When B is very large, and we call it trivial solution, here. This is what happened here for B, large, okay? But so what is this? So it happened that you say for B in this situation, for instance, But as I answered to Benoit, when we put P large and we don't have a steady state, we observe it for the finite right. So this means that tends to something which is a Plateau distribution, I'm pretty sure. I don't know how to prove it, but I'm sure that it's a Plateau distribution because the finite right is increasing and increasing. And if you put large delay, you go to something which is increasing and increasing, okay? As I said before, and pass for something which is very close to that we call it pseudo-equilibrium, which is this one, okay?
I see.
This one.
And another question related to the work in progress. What's your, I mean, what do you think about would be the meaning of this physical solution at the level of the PDE?
You say the physical, I think that they have to be a discontinuity of in the B reset.
So you will mean that
yeah.
like weak solutions with allowing discontinuity of B
Yes,
reset?
I think so. Yeah. And also maybe we have to think what is the reset value. Okay.
Okay, thank you.
Hello, again about this plateau formation. So you mentioned that the entropy method doesn't work. So is it possible to have a result of stability, for instance, when you start from a solution close to a plateau?
Yeah, but the problem is a plateau is not formally a steady state. So it's not easy to work with it because we don't know what is the equation for the plateau distribution. Okay. I think first we have to give a sense of a physical solution to try to use entropy method. I think so.
Okay, thank you.
When you have the periodic solutions with the refractory period and blow up, like it blows up and then it blows up again and you have periodic movement, can you see what you have in the refractory state just after blow up? Like what quantity of the network?
You say, sorry, I don't.
Yeah, when it blows up.
In this,
just after the blow up. What is the value of the refractory state? How many neurons are there in the refractory?
I think all
of them.
Yeah, sure. Because the blow up at the level of the particle system means that all the network synchronize, spike at the same time.
Yeah, it was my question because it was not obvious that all of the neurons would be in it. It could be half, or I don't know.
Yeah, maybe yes. Yes, I agree. Yes, maybe yes.
Okay, thank you.
Thank you.
Is there any other questions? Okay, if not, let's thank Maria for a nice talk.
Thank you. Thank you very much.